We're going to take a look at neurotransmitters, and we're going to specifically just look at acetylcholine first in this video. Acetylcholine is found in cholinergic neurons, which are found throughout the peripheral nervous system and also in the central nervous system. So acetylcholine is widely used throughout the nervous system. And you can see why they're called cholinergic neurons because of the word acetylcholine. And acetylcholine, this neurotransmitter, is going to be made in the axon terminal. And it's made from acetyl-CoA, which you might recognize as the part of the aerobic respiration pathway. It's what gets fed into the Krebs cycle. And then also something called choline, which is a relative of the B vitamins. And then there's an enzyme that will put those two together to form acetylcholine. You do not have to memorize the enzyme or this pathway. It's just to show you how it's made. But I do want you to know how acetylcholine is broken down. So there's an enzyme called acetylcholine esterase, and that will break down acetylcholine in the synaptic cleft after it's been released from the axon terminal. And let's just take a look at a picture here. So here's our cholinergic presynaptic neuron and the axon terminal. This is where the acetylcholine neurotransmitter will be made. And then the acetylcholine will just be packaged up into some vesicles, some little membrane-bound sacs, and then they will just be stored in the axon terminal until the action potential reaches the axon terminal and the voltage-gated calcium channels are opened, and calcium comes in and stimulates the exocytosis of the acetylcholine into the synaptic cleft. And then the acetylcholine will diffuse across the synaptic cleft to whatever this postsynaptic cell is. Maybe it's a neuron, a muscle cell, or a gland. And the acetylcholine will then bind to a cholinergic receptor. And then we don't want to keep getting a response in our target cell. So we do need to get rid of the acetylcholine neurotransmitters. So here's our enzyme acetylcholine esterase, which will then chew up and destroy the acetylcholine. And the choline just gets pumped back into the axon terminal. We'll reuse that. And then the rest of the part of the acetylcholine just diffuses out and just gets taken away and disposed of. So that's how acetylcholine is made and how it's released, and then how it's also broken down. All right, so this is really important. There are two different types of cholinergic receptors that are found on the target cell that acetylcholine will bind to. And it's really important to note that it's the type of receptor that determines the response that we're going to see in the target cell and not the neurotransmitter. Because you can have the same neurotransmitter acetylcholine, but you can get totally different responses in your target cell because you've got different receptors that the acetylcholine is binding to. So we'll see that. All right, so the two cholinergic receptors that acetylcholine can bind to that you need to memorize. We have nicotinic cholinergic receptors and muscarinic cholinergic receptors. The nicotinic cholinergic receptors are ionotropic receptors, which means that they are ligand-gated ion channels, okay? And they are specific for sodium ions, so they're going to let sodium ions in when acetylcholine binds, opens the gate, and so they're always going to be excitatory, and they're going to be creating depolarizing graded potentials, or EPSPs. The reason they got their name is because nicotine will also bind to these nicotinic cholinergic receptors in addition to acetylcholine. And then the muscarinic cholinergic receptors are totally different. They're metabotropic receptors. Remember, metabotropic receptors are G protein linked receptors. And they could be either excitatory or inhibitory, depending on what the G protein does. So it could create an EPSP or an IPSP. How the muscarinic cholinergic receptors got their name is because muscarine, which is a toxin found in some poisonous mushrooms, also binds to muscarinic cholinergic receptors in addition to acetylcholine. All right, so let's just take a look at some pictures. Here is a nicotinic cholinergic receptor. We're going to be talking about these a lot more later on. We find these, for example, in the skeletal muscle cells. So here we have acetylcholine binding, and this is a ligand-gated ion channel, so it's an ionotropic receptor. And when acetylcholine binds, it opens the gate. And these are specific for sodium ions. So mostly sodium ions are going to rush into the cell. There is a little bit of potassium that will leave the cell, but it's mostly the sodium ions coming in that's going to create the change in the membrane potential. So if sodium ions are coming into the cell, what does that do to the membrane potential? So remember, that's going to make the membrane potential more positive. So we're going to depolarize the cell and create an EPSP, or a depolarizing graded potential. So nicotinic cholinergic receptors are always going to be excitatory because they're letting in sodium ions. All right, and here's a muscarinic cholinergic receptors. So these are metabotropic receptors. They're a G protein linked receptor. So we've got acetylcholine binding to our muscarinic cholinergic receptor, our G protein linked receptor. That'll activate our G protein. And remember, the G protein can go do one of two things. So part of it could take off and go open or close an ion channel, and that could cause the cell response. Or the G protein could take off, turn an enzyme on and make some second messengers, and then that could cause the cell response. So depending on what the G protein goes and does, it could create either an excitatory or inhibitory response. So it just depends. All right, so very important to point out that we answer our question here. So we've got the same neurotransmitter, acetylcholine here, but we have very different effects. So acetylcholine will excite skeletal muscle and make it contract, but acetylcholine actually inhibits cardiac muscle and makes it contract slower. So how could the same neurotransmitter cause opposite effects? So to answer our question, why can the same neurotransmitter have different effects? It's because there's different receptors. Okay, so because we've got two different receptors for acetylcholine, we can get some different effects. So in skeletal muscle, we have a nicotinic cholinergic receptor. Remember, those are always excitatory. They're ionotropic receptors, and when acetylcholine binds to this ligand-gated ion channel, open the gate, sodium ions come in, and that's going to depolarize this skeletal muscle cell, and that will lead to muscle contraction. And then in the cardiac muscle, we've got a muscarinic cholinergic receptor. So when acetylcholine binds, we activate the G protein linked receptor, the G protein takes off, and we end up opening up some potassium channels. And remember, potassium always wants to leave the cell. And if potassium is leaving the cell, what does that do to your membrane potential? So remember, it's going to make it more negative inside. So if potassium is leaving with its positive charge, we're going to hyperpolarize that cardiac muscle cell, and that's going to inhibit contraction and actually slow the heart rate down. So the heart's going to beat slower. So in this case, the muscarinic cholinergic receptor has an inhibitory effect. So acetylcholine is excitatory to skeletal muscle, but acetylcholine on cardiac muscle is inhibitory. And it's because you've got different receptors. Even though you have the same neurotransmitter, but because you have different receptors, you can get different effects.